This is the second class on the theory of small oscillation. In the earlier class, we have introduced the subject small oscillation and mainly discussed the stability of an equilibrium point. Um, we confined our discussion to the stability analysis of one-dimensional system. What we have done in the last class is that we consider a system which is a conservative, so can be represented by a potential, and for an equilibrium condition, there no force acts on the system, and the equilibrium point may have different types like stable equilibrium, unstable equilibrium, metastable equilibrium, or neutral equilibrium. The characterization of these can be done by containing higher order derivatives. As the force, generalized force Qi acting on the body is given by del V, del Qi. And in the equilibrium condition, this force is given by del V, del Qi at this point, equilibrium point, that is at 0. And this is 0. So the first derivative of the potential is 0 at an equilibrium point. The nature of the equilibrium point is determined by the second derivative. As we know, for one-dimensional problem, if del V, del 2V, del x2 is equal to 0, then it is a neutral metastable equilibrium. It is a metastable equilibrium point. If it is greater than 0, then it is a stable equilibrium point, and if it is less than 0, it is an unstable equilibrium point. And for neutral equilibrium point, the potential remains constant all along. We applied the theory in one-dimensional cases. Today we shall cite two very popular examples of one-dimensional case, and then we shall continue our discussion of stability analysis for more than system having more than one dimension. So firstly, we consider a simple planar pendulum. This is a very common example of physics, classical physics. It comprises of a string of fixed length and a bob is suspended by means of the string, and this angle theta is the only generalized coordinate. If we said here the potential energy is 0, then the potential energy of a bob of mass m suspended by a string of length L is given by V of theta is equal to mg L 1 minus cos theta. This much is the mg. This is the potential energy. Sorry, we have taken, this is the 0 level of potential energy. So this is the 0 level of potential energy. This much distance, this is the 0 level of potential energy, and this is the change in height. This much is L, and this is L cos theta. So this is the change in potential energy. So to study the stability, we calculate del V, del theta. This is equal to mg L sin theta. And for equilibrium point, we must have sin theta is equal to 0, which gives theta is equal to 0. That is, the equilibrium point is one for which the bob is vertically right below the point of suspension. To analyze the nature of the equilibrium point, let us calculate this one, which is mgl cos theta, and this is equal to mgl at theta is equal to 0, and this is, since this is greater than 0, this point is a stable equilibrium point. So, which is a stable equilibrium point. Now we consider another example, that is the spherical pendulum. A spherical pendulum is also a point mass m suspended from a fixed point by means of a string of fixed length, and the bob can move on the surface of a sphere spherical pendulum. So we have a string, this is our coordinate system, right-handed coordinate system, x, y, z. We have a string of length L whose one end is fixed, and this point is taken as the origin of the coordinate system, and the other end, on the other hand, there is a mass point M. The coordinate of the mass may, when represented in spherical polar coordinate, is r theta phi, where phi, theta is this angle, and phi, as usual, the phi is this angle. If we consider z is equal to 0 plane to be the 0 level of potential, so V at z is equal to 0 is equal to 0. This gives us V as a function of theta, theta as mgz is equal to mgl cos theta, where we have taken z is equal to 0 as the 0 level of potential. At a particular instant, the z component of the bob is z, which is L cos theta, so this is the potential. So the first derivative of it is del V del theta is equal to mgl sin theta. So for equilibrium point we have sin theta is equal to 0, sin theta is equal to 0, which indicates theta is equal to 0 or pi. In the earlier example, we have ignored the option of pi because simple pendulum rotates to and fro with small amplitude about its equilibrium point. But for a spherical pendulum, it can move everywhere on the surface of a sphere, so both the values are included. So if we calculate the second derivative, so the equilibrium point is these two. One is when the particle bob is over here. This is one equilibrium point 1, and other one is the equilibrium point 2. So this point we have denoted as E1, equilibrium point 1, and this is E2. And del 2V del theta 2 is equal to minus mgl cos theta. This is equal to, taking this positive quantity out, this is minus 1 for theta is equal to 0, and this is plus 1 for theta is equal to pi. So this point is basically that point E1. This is the E1 point, and this is the E2 equilibrium point E2. Since this is G positive, this is a stable equilibrium point, and this is an unstable equilibrium point. So we see that it is an unstable equilibrium point, and this is a stable equilibrium point. If we slightly displace, when the bob is on the positive z axis, no gravitational force, this is an equilibrium position, and if we slightly displace it from here, the particle will move away from the equilibrium point. So there is a tendency that when perturbed slightly, it moves away from it. On the other hand, if you perturb the system from E2, slightly from E2, there is a tendency that the particle comes back to the point E2. That's why it is a stable equilibrium point. So much about the stability of one-dimensional system. For if we have a system having more than one dimension, say two-dimensional problem, we know the specific prescription for finding out the stationary points of a function and to justify its nature of the stationary point, that is whether the stationary point is a maxima or minima. However, here we shall recall that we have recall a more general treatment. Consider a function v, which is a function of n coordinates x1, x2, xn. We write it in short and v as a vector x, and we see that the stationary points of v is x0. The stationary point as x0, it is a vector. We write the vector to be, this is x10, x20, x30 up to xn0. So what is the characteristic of this stationary point? That at the stationary point, del v, del xi, and if we denote this in short, if at x is equal to x0 is 0 for all I. For all I in the range 1 to n. This is the definition of stationary point. And the characterization of stationary point, so we can expand v of x, v of x about the stationary point as v of x0 plus summation over I is equal to 1 to n del v del xi at x0 times xi minus xi0 plus half summation over ij, both running from 1 to n, del 2v del xi del xj evaluated at x0, xi minus xi0, xj minus xj0 plus higher order terms. We at the stationary, by the definition of stationary point, this is 0, so we write it df is equal to v at x minus p at x0 is equal to half of this thing, which we call at Vij, and this much we call eta I, eta j, where eta I is defined as xi minus xi0. That is the departure from the corresponding equilibrium configuration. And if the point under consideration is a maximum point, then it is maximum. This value is maximum, so this is going to be, if it is a maximum point, this is 0 for me. If x0 happens to be a maximum point, then the v and x0 is higher than this, so and for point of inflection, this is equal to 0 for saddle point. We have learned earlier that this equation df can be written as is equal to half summation over k is equal to 1 to n ak modulus square times lambda k, where lambda k, they are the eigenvalues of matrix B. If we consider these are the components of the matrix, so we can consider a matrix B which is B11, B12, B13, B21, B22 up to Bn1, Bn2, Bnn. This is a matrix, and this is a square matrix because both I and j runs from 1 to n. So for a system with finite degree of freedom, it is a square matrix and it is a real symmetric matrix. So it is the Hermitian matrix, and so all this is a real symmetric matrix. So we know that they are the B is the Hermitian matrix, and the eigenvalues of Hermitian matrix are real, always real. Now, if all the lambdas are non-negative, then this quantity is either 0 or positive. If at least one all the eigenvalues of V are non-negative, and if at least one of them is positive, then this quantity is 0, greater than 0 sort of point corresponds to a minimum. And on the other hand, if all the eigenvalues of V are negative, then it corresponds to a maximum. But no such simple conclusion can be drawn when the eigenvalues of the V matrix have mixed signs. However, we shall here present few systems in 1 and 2 and 3 dimension when the eigenvalues have specific sign, and so that this theory can be applied to find the stability. As the first example, we consider two-dimensional problem in which 2 point mass, identical point mass, each of mass m, are connected by 3 identical elastic springs, and the combination is kept on a smooth horizontal table and fastened between 2 rigid supports. So this is our problem system. This length is fixed. This is mass 1. This is mass 2.2. Mass each one has the mass. The equilibrium configuration is these are 3 identical springs, each of spring constant K, elastic spring. When this particle, at the equilibrium situation, the particle is over here and its coordinate is x1 and x2. When it is displaced x1 0 and x2 0, if it is slightly displaced, so this comes over here, then the position of it is denoted by x1. So displacement of the particle from the equilibrium position is denoted by eta I. Similarly, eta 2 represents the displacement of particle 2 from its equilibrium position. So here we consider eta 1 and eta 2 are the generalized coordinates. The potential energy here is a function of eta 1 and eta 2. This for this it is half k eta 1 square. For this it is half k eta 2 square, and for this it is half k eta 1 minus eta 2 square. So this is the potential energy. Now, as for the theory that I have just recalled, we are to construct a P matrix. Here, the P matrix will be a 2 by 2 matrix. So we first define V1 as V1 is equal to del V del eta 1. This is K eta 1 plus K from this eta 1 minus eta 2 is equal to K twice eta 1 minus eta 2, and V2 is equal to del V del eta 2 is equal to, from this it is K eta 2, and from this it is K eta 1 minus eta 2, and with a minus sign, so that this is again K twice eta 2 minus eta 1. So first equilibrium point. For equilibrium point, here we shall call configuration. Equilibrium configuration, we have del V del eta 1 is equal to 0, del V del eta 2, which gives us eta 1 is equal to 0, eta is equal to eta 2. So the stationary point is eta 1 and eta 2 0, that is the equilibrium point when the respective masses were at their equilibrium position. From this we can calculate V11 is equal to del 2V del eta 1 2. So if we differentiate it, this gives you just 2K, and similarly V22 is V22 is equal to del 2V del eta 2 2, which can be obtained from here. It is again 2K, and V12 and V21 are same. V12 is equal to V21, which is del 2V del eta 1 del eta 2. This can be obtained either from here or from here. This is minus K. So the P matrix that we were looking for is V11, V12, V21, V22. This is taking K common. 2 minus 1, 2 minus 1, minus 1, 2. This is the P matrix. And we are to find out the eigenvalues of this matrix. So, for eigenvalues of V, we say that this is 2K minus lambda minus K, 2K minus lambda, this determinant is 0, so that we have 2K minus lambda is equal to plus minus K, or lambda is equal to K or 3K. Since we are dealing with the spring constant K, see this constant is positive. That is, whenever the particle moves towards the right of the equilibrium point, each of the spring tries to send the particle back to the equilibrium position. Or in other words, if we call restoring force F is equal to minus Kx. So K is a positive quantity that shows that each of the eigenvalues are positive. So eta 1 is equal to 0 is equal to eta 2 is a stable equilibrium point. Stable equilibrium point of the system. Now we shall consider another example, which is a linear triatomic molecule. So another problem of this sort. This is a three-dimensional problem. That is, we consider a linear triatomic molecule. Say, for example, carbon dioxide molecule. in which case there at the center there is one atom and other on the either side of it there are two other atoms. So this is as for example we consider CO2 and we consider its vibrational aspect. We consider the vibrational motion, but model is like that. We have a carbon atom like this, sorry, oxygen atom. There is another carbon atom. This is the system. Now, in the equilibrium condition, so we have a linear triatomic molecule. In the equilibrium separation, there is a fixed distance separating the carbon atom with oxygen atom. Since these two are identical, the situation is symmetric about the carbon atom. Let the equilibrium separation be D when the separation between the carbon and oxygen atom, that is this bond length increases above D, then attractive force acts which tries to bring the atom to its equilibrium point, and due to inertia the bond length decreases beyond the equilibrium separation and then a repulsive force acts. We have already encountered Leonardo Jones potential which can explain such behavior. The typical graph of Leonardo Jones potential is of this sort. This is the potential V and this is the separation, say R for three-dimensional case. So, and you know that force F is equal to minus R del V del R. In this region, as R increases, V decreases. So in this part, if we consider this one, in this part the force is repulsive. A repulsive force acts. And for on this side, as R increases, V decreases. So del V del R is del V del R is negative to so this is an attractive force. Here acts an attraction. So when they are just over here, this is the equilibrium separation D that we have called D. If the separation between the atoms is greater than D, then there will be a tendency that they will come closer. When they comes at a separation less than D, there will be a tendency to move them apart. So in this way, each bond vibrates about their equilibrium position. We could model this system as if they are connected by a simple elastic springs of spring constant K, and these are the masses of oxygen atom are denoted by small m, and that of the carbon atom is denoted by capital M. So if we consider eta 1, eta 2, eta 3 are the equilibrium separation of the atoms, then this is x10, this is x20 and x30, and the displacement from it is denoted by x1, the displacement is x2, and displacement of third is x3. So we define eta I. Eta I is equal to xi minus xi0 where ions from 1 to 1, 2, 3. So potential energy V of the particle, which is a function of eta 1, eta 2 and eta 3. This is for this spring. The elongation or compression of this spring is given by eta 1 minus eta 2. So potential energy is square of the deformation. So this is the potential energy, and for the other part string, for this spring, the potential energy is half k eta 2 minus eta 3 square. So this is the potential energy. So firstly, our aim is to find the equilibrium point, that is the stationary points. So we find del V del eta 1, which is V1 in our notation. This is k eta 1 minus eta 2. Then V2 is equal to del V del eta 2. This is k, from this part it is eta 2 minus eta 1, because there will be a minus sign which has been adjusted over here, plus k eta 2 minus eta 3, and finally V3 is equal to del V del eta 3 is equal to k eta 3 minus eta 2. So for equilibrium position, this is 0, this is 0 and this is 0. So which gives us the equilibrium configuration. Because this particle is, this system has been described in configuration space, equilibrium configuration is eta 1 is equal to eta 2 is equal to eta 3 is equal to 0. This is the equilibrium configuration. Now our aim is to study what is the nature of this equilibrium configuration, whether it is a stable equilibrium or an unstable equilibrium. For that, we need to calculate the matrix elements of V, which are V11 is equal to del 2V del eta 1 2. This is simply K. V22 is equal to del 2V del eta 2, which is 2K, and del 2V, sorry, this is V33 first one. V11 and V33 are symmetric. This is K. Now, the cross elements, these are the diagonal elements of the matrix B. Now, V12 is equal to V21 is equal to del 2V del eta 1 del eta 2. So we can differentiate this with respect to 2 and we get this is minus K. Then we need to know V23 is equal to V32 is equal to del 2V del eta 2 del eta 3, which can be obtained from this one by differentiating this with respect to eta 3, and the result is minus K. And finally, V13 is equal to V31 is equal to del 2V del eta 1, del eta 3, this is 0. So we get the matrix for V. The matrix for V is, now the V matrix V V11, V12, V13, V21, V22, V23, V31, V32, V33. This is the 3 by 3 matrix, and this is equal to V11 is K, V12 is minus K, V13 is 0, V13 is 0, V21 is minus K, V22 is 2K, and V23 is minus K, and V31 is 0, this is 32, V32 is minus K, and V33 is plus K. So this is the matrix. And the eigenvalues of this are obtained. Eigenvalues of matrix B are obtained from this determinant K minus lambda minus K 0 minus K 2K minus lambda minus K 0 minus K minus lambda from this determinant. So we evaluate, I am just erasing this part, and the determinant can be evaluated. This is K minus lambda, taking this part, then this multiplied by this, 2K minus lambda, K minus lambda minus K square, and from this part minus K, and then this is basically this multiplied by this plus this part. So this is K into K minus lambda. This is equal to 0. If we take K minus lambda common, then we have this part, and this is minus K square. So we have 2K square minus 3K lambda then we have lambda square plus lambda square, and this is case, there is 2K square, and this is K square, and this K square minus 2K square is equal to 0. Or we have lambda, K minus lambda, and then we have this from this part, this is lambda minus 3K is equal to 0, which gives lambda is equal to 0, K and 3K. These are the eigenvalues of the vector of the matrix V. And we see that none of the eigenvalues are negative. One is 0 and other two are positive. So we see that since the eigenvalues are non-negative, so the point eta is equal to 1, 1, 1, that's stable equilibrium point. So this equilibrium point is a stable equilibrium point. So which denotes that eta I is equal to 0 corresponds to a stable equilibrium point. So such types of analysis can be continued for other types of system. I am giving another problem for you to work out yourself. This is also a three-particle system. Three-particle system where the three identical mass are arranged symmetrically on the circumference of a circle of radius A. So we have a circle of radius A, and there are three masses, 1, 2, 3. These three mass points, and these mass points are connected with each other along this circular ring, springs, elastic springs, as if they are connected by elastic springs. And we are to consider the vibrational aspect of this system. Obviously, the deformation of the, if we can denote theta 1, theta 2, theta 3 as the generalized coordinates, which represents the displacement of the angular displacement of the particles from their respective equilibrium position, then the elongation or compression of this ring is determined by the factor A, theta 1 difference theta 2. Similarly, for this, it is the elongation or contraction is given by theta 2 minus theta 3, and this is from, so the potential energy, which is a function of theta 1, theta 2, theta 3, is half k times, for this spring, the k a square, k a square times theta 1 minus theta 2 whole square plus theta 2 minus theta 3 whole square plus theta 3 minus theta 1 whole square. Homework is to find out the equilibrium position, find equilibrium configuration, and analyze its stability. This is all about the stability analysis. I have purposefully has paid more attention on the stability analysis, because the entire theory of small oscillation that I will be presenting from the next class onwards depends on the oscillation of a system about its stable equilibrium configuration. The theory that will be presented is not valid if the equilibrium configuration is an unstable one. That is why I am emphasizing the point, the stability of the equilibrium point.